All right, let's take a look at Chapter 5, Numeration Systems, Section 5.3, Calculating and Other Bases. In this section, we're going to want to count a non-base 10 system, state similarities between a base 5 and a base 10 system, perform arithmetic operations in a non-base 10 system, and make conversions among binary, octal, and hexadecimal systems. Non-base 10 systems. In base 10, place value corresponds to powers of 10. 1, 0, for example, is 1 times 10 to the power 1, and 0 times 10 to the power 0. In base B, place values correspond to powers of B. So 1, 0 is one group of B to the power 1 and no groups of B to the power 0. Base 5 uses digits 0, 1, 2, 3, 4. In base 5, we start by counting 1, 2, 3, 4. At 5, though, we must rewrite 5 as 1, 0, base 5. Base 5 does not use the digit 5. 1, 0, base 5 equals one group of 5 to the power 1 and no groups of 5 to the power 0. Following this pattern, we count thus: 1, 2, 3, 4, 10 base 5, 11 base 5, 12 base 5, 13 base 5, 14 base 5, and 20 base 5. 20 base 5 is two groups of 5 and no groups of 1. So reading through our first numbers, we have 1, 2, 3, 4, one group of 5, 1, 5, and 1, 1, so 6, 1, 5, and 2 ones, 7, 1, 5, and 3 ones, 8, 1, 5, and 4 ones, 9, 2 5s, which is a 10. 2 5s and a 1 is 11. 2 5s, 2 1s is 12, and so on, until we get to a number like 44 base 5. That's 4 groups of 5. That's 20 plus 4 units, so 24. So at the number 25, right, we have 1, 0, 0. That is one group of 5 squared for 25 and no groups of anything else. The base 8 or octal system uses digits 0, 1, 2, 3, 4, 5, 6, 7. The counting pattern is 1, 2, 3, 4, 5, 6, 7, 1, 0 for 8, 1, 1 for 9, 1, 2 for 10, right? Let's look at the number 17. 17 base 8 is 1, 8, and 7 units. 1, 8, and 7 units is a value of 15. If we add one number to that, then we get the number 16, which is two groups of 8 and no units, so 20, 21. 77 is 7 groups of 8 and 7 units, right? 7 groups of 8 is 56 plus 7 units is 63. Add 1, we get 64. 64 is 8 cubed. 8 squared. 8 squared. So one group of 8 squared plus no groups of any other. The base 16 or hexadecimal system uses the digits 0 through 9, but then we need something for 10, 11, 12, 13, 14, and 15. So we use A, B, C, D, E, F. The counting pattern is 0 through 9 as we understand it, and then A is 10, B is 11, C is 12, D is 13, E is 14, F is 15. So a number like 1, 0 is one group of 16, no units. A number like 1, 1 is one group of 16, 1 unit, 17. And IF is one group of 16 plus 15 for 31. FF is 15 groups of 16 plus 15. The base 2 or binary system uses the digit 0, 1. The counting pattern is 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1. And this is the doubling system we saw in the, what was it, Egyptian? I forget which one it was, but we saw the doubling. We saw this base 10, this base 2 system come up in the concept of doubling. All right, let's see. Now let's convert, right? Change. So we're going to change 4,302 base 5 to decimal notation. So Hindu Arabic and decimal notation and place value, place 10 system, those are all the same words. So sometimes they're asking us to convert it to Hindu Arabic. That's our system. Sometimes they're asking us to translate something, to convert something to base 10 notation. That's our system. And base 10 is decimal. That's what decimal notation means, base 10 system. So our decimal system, our base 10 place value system, is the same thing as the Hindu Arabic system. That's the same system. So they keep changing the name on us, but they just keep meaning our way of thinking. So convert the 4,302 in base 5 to our way of thinking. So our decimal notation. To convert to decimal notation, we write 4,302 base 5 in expanded notation, right? Just like we did with ours, only with base 5. So 4,302 base 5 is 4. Well, I like to read it the other way. 2 groups of units, no groups of the base, 3 groups of base squared, 4 groups of base cubed. Our base is base 5, so that's 4 times 5 cubed plus 3 times 5 squared plus 0 times 5 to the power 1 plus 2 times 5 to the power 0, which equals 4 times 125 plus 3 times 25 plus 3 times 5 plus 2 times 1, which is 500 plus 75 plus 0 plus 2 for 577. Write 384 as a base 5 numeral. Notice there's no little subscript on the number. That's our base 10 system. We do not write little subscripts on our number. So if there's not a subscript, you're writing a base 10 number. If it's not a base 10 number, you need a little subscript in the bottom right lower digit, right, on the lower end of the digit, so that you can see, you can tell your reader what base system they're actually using. So if you divide 385 by 5, you'll get 75 with 4 units left over. So this method, we're just going to repeatedly divide by 5. Next, divide. Is there a typo? Because we had 75 in the first one, and now we divide 76, which doesn't make sense, but maybe one of those numbers is wrong. Next, we divide the 75 or 6 by 5. This is equivalent to dividing the original number by 25, which is 5 squared. From this division, we see that after dividing 25, there is 5 left over. This means that the base 5 numeral, there will be 1 in the 5's place. We continue this process and express the divisions more compactly. So it was the 75 they decided was the wrong number. So in that previous slide, the 75 should be a 76. So instead of going upward, they go downward. So first they take the original number, 384, they divide by 5. They got 76, remainder 4, which goes into the units location. the remainder, this time not the quotient. The quotient is the thing we keep dividing into in this method. So although this is like converting in the Babylonian method, it's a there this is a different process. You could do the same thing, start with the largest power of 5 and divide like we did with the 60s, or you could take this method that they're using here and apply it to the Babylonian, therefore just dividing by 60 repeatedly and having this process. So it's two processes that are doing the same thing, converting our number to another base. So in this system, they repeatedly divide by the base, and that's how they find the answer. So divide 384 by 5, you have remainder 4. That goes in the units location. And then you divide into the quotient, which is 76. Divide 76 by 5, you get 15 with a remainder of 1. The 1 goes into the next position, which is the 5's position. So units 5's, 5 squared, 5 cubed, working from right to left. Now we go into the remainder, 15. We divide the remainder 15 by 5. We get a quotient of 3, remainder 0. So a 0 goes into the 5 squared location. Now your remainder 3 isn't a 0 yet. You have to stop when you hit the quotient 0. So 3 divided by 5 gives you a quotient of 0 because you can't get any groups of 5 out of a 3, right? So we have 0, remainder 3. Once we hit the 0 and the quotient, we stop because now we just hit zeros forever. And you have your last remainder, which is 3. That goes in your 5 cubed location, and you read it in the reverse order. So you read the remainders in reverse. 3014 base 5 is our number. So 384 in a value as a number is our numeral 384. And for base 5 system is 3014, little subscript base 5. Add 342 base 5 to 223 base 5. The solution. We add much like we do in performing decimal addition. First, we add the units, right? So stack it like the traditional borrowing, carrying algorithm and start at the unit location, work your way to the left. So we add much like we do in performing decimal addition. First, we add the units 2 plus 3 to get 5, which is expressed as a 1, 0 in base 5. So we need to bring down the 0 and carry the 1 into the 5's place. Next, we have the numerals in the 5's place. The 1 that we carried plus 4 plus 2 equals 7, which written in base 5 notation is 152 units for a 7, right? So we bring down the 2, carry the 1. We finish by adding the numerals in the 5 squared place, carrying as necessary. So we add the 1 plus the 3 plus the 2, which gives us 6. In base 5, that's 1, 5, and 1 unit for an 11. You bring down the 1, carry the 1, but then that carried 1 has nothing to add to, so it just comes all the way back down, giving us a 1,120 base 5. Now, if you've accidentally left a 5 or a 6 down there, this would be your checking point because you don't use the numeral, the decimal digit, you don't use the digit of the base itself, right? So you aren't going to use a 5 or higher to represent a base 5 number. Subtract 143 base 5 from 424 base 5. Solution. Subtract in base 5 is also much like base 10 subtraction. We begin by subtracting 3 units from 4 units to get 1 unit. In the 5's place, we cannot subtract 4 5s from 2 5s, so we borrow 1 25 and we write it as 5 fives. Thus now we have 7 fives in the fives place, which we have written as a 1, 2, as shown in the figure. We complete the subtracting. We complete the subtraction by subtracting one group of 25 from the 3 remaining groups of 25. So when we borrow, in red here, borrowing 125, we now have 12 base 5 or decimal 7 fives. Subtracting, we get 3 fives. Multiply. Multiply 134 base 5 by 32 base 5. The solution. 5 units expressed as 1 5. Okay, so just like ours, right? We're going to do the 2 times 4 to get 6. Oh, no, we don't. 2 times 4, we get 8. 8 is then 1 5, 3 units. So 8 in base 5 is written 1 3. So we write our 3, carry the 1. Now we do 2 times 3 to get 6. Add the 1 to get 7. But this again is base 5, right? So we're going to write the 2, carry the 1, and continue this process. Just like our base 10. Performing division. Solution, we write several multiples of 23. So we write times 0, times 1, times 2, times 3, times 4. Also similar to that doubling method that we saw. From this list, we see that 23 divides into 41 once, but not twice. So we start the division by placing 1 in the quotient, right? So we isolate what we can, just like in the traditional long division algorithm. And once you're done with your 41, you bring that 3 down, right? So you have a remainder of 13. But now you bring your 3 down and you try to get into 133 with as many groups of 23 base 5 as you can. Thus 23 base 5 divides into 4,132 base 5 with a quotient of 131 base 5 and a remainder of 14 base 5. Write the binary command for 10110011011110 using octal notation. Solution. We begin by arranging the bits in 10110110110111110 in groups of 3 beginning from the right. Groups of 3 beginning from the right. We then interpret each group of 3 bits as an octal number, as shown here on the next slide. For the sake of efficiency, we often omit the subscripts that indicate the base. So although this does not have a little base 2, base 2 numbers look like this, just a bunch of zeros and ones, and so often they don't write a base 2 on there. I do anyway, because I heavily work in base 10. Write the binary command 1011001101101110 using octal notation. First, in groups of 3 from the right to the left, you break your number up, right? So we have a group of 110, a group of 011, a group of 101, a group of 001, a group of 011, and a group of 1. And then we look at the octal numbers, right? Because these are powers of 2. And so they've broken each number so that the first digit being the digit to the right, is 2 to the power 0. The middle digit is 2 to the power 1, and the last digit is 2 to the power squared, right? So, for example, when we count in binary, this is written here in octal, right? So we translate each group of 3 into an octal number for a 131536. Write the binary command 101100110110111110 using hexadecimal notation. We begin by arranging the bits into groups of 4. beginning from the right. So now we can get to a 16, not an 8, right? So we're going to arrange the bits in groups of 4 beginning from the right, giving ourselves groups of 1, 1, 1, 0, 0, 1, 0, 1, 0, 0, 1, 1, and 1, 0, 1, 1, reading from right to left. And in hexadecimal, we have B11, parentheses, so that you know it's an 11, 3, 5, E14. The final answer is B35E. B being 11, E being 14.